Welcome to this explainer. Today, we're taking something that usually looks like intimidating alphabet soup on a whiteboard, I'm talking about linear equations, and transforming them into incredibly relatable real-world tools. We're drawing directly from a junior high school alternative learning system, or ALS, lesson plan. And honestly, whether you're looking at a budget, planning a trip, or figuring out your paycheck, the math we're covering today is secretly running the show behind the scenes.
Here's our roadmap for today. We'll hit the real-life math hook, look at two forms of equations, figure out finding the equation, move on to graphing the line, and wrap it all up with real-world applications. Let's dive in.
Section 1. The real-life math hook. Let's see how we actually solve everyday problems using math.
Okay, so math is basically a practical toolkit, and this ALS lesson plan totally proves it. Picture this. You're hopping into a tricycle. The fare starts at a flat rate of 15 Philippine pesos, right? And then for every extra kilometer you travel, an additional 5 pesos is added on. Now, you intuitively know that the further you go, the more you're going to pay. But how do we actually map this relationship out so we can predict exactly what, say, a 20-kilometer trip will cost? Well, that brings us to the core concept here. Linear equations always, and I mean always, form a perfectly straight line to represent these real-life relationships. Whether you're measuring distance and time, or our tricycle fare and the kilometers traveled, a linear equation maps that steady relationship. If the rate of change is constant, that resulting line on your graph won't waver. It's going to be perfectly straight.
Moving right along to Section 2, two forms of equations. Time to understand the mathematical vocabulary that lets us write these relationships down.
So, we've got two common ways to organize all this data on paper. On one side, we have the standard form, which is ax plus by equals c, and on the other, the slope-intercept form, y equals mx plus b. Honestly, these are just two different frameworks for organizing the exact same mathematical truth. But for this explainer, we're going to focus heavily on that slope-intercept form, mostly because it literally tells you the story of how your line behaves just by looking at it.
Let's break that down a bit more. Y equals mx plus b. The absolutely crucial part here is knowing what these letters actually mean in the real world. So the m stands for the slope. You can think of slope as your constant rate of change. You know, the rise over the run. And the b? That stands for the y-intercept. Think of b as your baseline. It's your starting point before any changes even happen.
And this brilliantly illustrates our tricycle ride. Remember, the fare adds 5 pesos for every single extra kilometer. That constant rate of change, that is our slope. So in our equation, our m is simply 5.
And what about our starting point? Well, before that tricycle even moves a single kilometer, you already owe that base fare of 15 pesos. That 15 peso baseline is our starting point on a graph, which means it's our y-intercept. So our b is 15. See? Suddenly, those abstract math letters turn into very real money.
Let's keep building on this. Section 3, Finding the Equation. We'll look at 4 methods to solve the puzzle, depending on what clues you've got.
Depending on the specific clues you're handed, there are basically 4 scenarios you might face when trying to find your equation. You could get the slope and the y-intercept, the slope and just one point, 2 separate points, or the x and y-intercepts. Now, I know this might look a bit like a giant puzzle right now, but don't worry, we're going to walk through each one logically.
Okay, here's the first and definitely the most straightforward method. When you're directly handed both the slope and the y-intercept, honestly, it's a gift. If your slope m is 2 and your y-intercept b is 3, you just substitute them right into our y equals mx plus b formula. Boom, the result is y equals 2x plus 3. It's really that simple. Just plug and play.
But what if you have the slope, and instead of the starting point, you just have one random location on the line? Say we have a slope of 1 and an ordered pair of 2, 5. For this, we use a bit of algebraic scaffolding called the point-slope form. By plugging our numbers into this temporary formula, we can do some quick algebra to isolate y. And once you solve it, it neatly transforms right back into our comfortable slope-intercept form, y equals x plus 3.
All right, on to the third method. Let's treat this one kind of like a detective story. Imagine you only have 2 points on a map, 1, 4, and 3, 8. You are entirely missing your slope. So you've got to calculate it first. Remember, slope is rise over run. We take the difference in our y values, divide that by the difference in our x values, and that gives us a slope of 2.
Now that we've found our missing clue, it's exactly like the previous method. Just substitute one of those points in, and you get y equals 2x plus 2.
And our fourth method involves x and y-intercepts. Now, intercepts are brilliant clues in disguise. If the y-intercept is 2 and the x-intercept is 4, they aren't just random numbers. They're actually giving you two exact coordinates, 0, 2 and 4, 0. Once you plot them, you just follow the exact same detective work from our last step. You find the slope between those 2 points, and you write the equation. Easy, right?
Moving right along to section 4, graphing the line. Let's translate all this pure algebra into clear visuals.
Translating this to a graph on a Cartesian coordinate plane just requires a few clear steps. Let's say we want to graph y equals 2x plus 3. Every single time, you're going to start by plotting the y-intercept first. So put a dot at 0, 3. Next, use your slope of 2 to find the next point. You rise up 2 spaces, run 1 space to the right, and drop your second dot. Then, just draw a straight line right through them, label your axes, and you've literally just mapped your equation.
And finally, we've reached section 5, real-world applications, taking the math beyond the classroom.
You know, linear equations are deeply integrated into our daily lives, even if we totally don't realize it. In business, you use them for pricing out total costs. For travel, they calculate your fare based on distance, so you know exactly what you owe the driver. They map out your paycheck based on an hourly wage. They even integrate into values education, helping you honestly compute and plan out your daily savings goals over time. It's everywhere.
The source lesson plan we're looking at includes this fantastic wrap-up exercise called an exit ticket, and I highly encourage you to try it out yourself. Just grab a piece of paper and write down 3 things. One specific thing you learned today, one step you feel you kind of still need to practice, and one real-life use of linear equations that applies directly to your own life.
And I'll leave you with this final thought-provoking question to chew on. If you track your daily savings for a week, what does your personal linear equation look like? What's your starting baseline, your b? And what is your steady rate of daily saving, your slope, m? Because math isn't just stuck on a whiteboard, it's mapping your daily routine. Thanks for joining me on this explainer, and keep looking for the hidden equations in your world.